So let's look at what happens to conformation when we put substituents on a cyclohexane.
If I have a cyclohexane ring with one substituent group, so just one methyl group. That methyl group, again, could be in either the axial or equatorial position. So here it is in the axial position, this in the equatorial position.
At equilibrium, we know that the concentration of the equatorial conformer is higher than that of the axial conformer. So that means that the ring is preferentially in this state where the substituent is in the equatorial form. The reason for that has to do with some van der Waals strain that can occur when substituents are in an axial position. Hydrogens across on the ring at positions 3 and 5 can form some van der Waals strain with groups, hydrocarbon groups, when they are in an axial position. However, when these are in an equatorial conformer, they lack that interaction. And so this conformation is the more favorable conformation. If we wanted to look at this, again, using a Newman projection, you can see here is the ring when the methyl group is in an axial position. Here it is, there's an axial up. And what you see is that it is gauche to the hydrogens here, the CH2 group. So you have some strain occurring there. However, when we put it in an equatorial position, which would be down here, there are no gauche interactions. You can see everything is staggered. Other monosubstituted cyclohexanes follow the same pattern, which is that the equatorial conformer is more stable than the axial conformer. So here are some other substituents, and you can see the percent of the axial versus equatorial versions. So as you go from something like fluorine, which is almost equal, but still favorably more equatorial, to bigger groups. So the bigger the group gets. So we go from methyl and then add on, this is a isopropyl, etc. If we make the group bigger and bigger and bigger, we see that the percent equatorial favorability dramatically goes up. So to help the ring from being destabilized from that gauche interaction, the equatorial positioning of the ring becomes almost completely the only version that is utilized. So let's move on to conformational analysis of disubstituted cyclohexanes. So instead of just one group on a cyclohexane, what happens when we add two groups? So we said substituents on a cyclohexane, what is disubstituted, of course, can be axial or equatorial. And they can have a cis or trans nature. We already kind of brought that up with the question before. But we do also see cis and trans in cyclohexanes. So to determine which chair conformation of a disubstituted cyclohexane is more stable, you have to compare the number and the sizes of equatorial substituents. So for example, here is a trans 1,4-dimethyl cyclohexane. Let's break this up just so you understand the name to the ring. Notice that this is in position 1, 2, 3, 4. So we have a methyl group on positions 1 and 4 on a cyclohexane. And they are both axial here, but the point of them being trans is that one is facing up and one is facing down. Now, this trans cyclohexane can also be in a position where this is up but equatorial, and this is down but equatorial, and this is up but equatorial. So it's still trans. One is down and one is up. Here, one is down and one is up. So in this case, we have a difference between both methyl groups being axial or both methyl groups being equatorial. So the ring is going to favor the di-equatorial conformer. Remember, substituents are more favorable in the equatorial position to limit that van der Waals interaction, that steric interaction that occurs. Okay, but what about the cis version? So here we have a cis version. Here, one methyl group is in the equatorial position, but it is up. So it is equatorial, but up. And this one is axial, but up, right? So that makes it cis because both are up, even though one is equatorial and one is axial. When this goes through ring inversion, this group becomes axial and up, and this one becomes equatorial and up. So as you can see, these two rings, because the groups are the same, are equal in energy. That's because here we have a methyl group that's equatorial up and a methyl group that's axial up. And here we also have a methyl group that's equatorial up and a methyl group that's axial up. So generally, when you compare this particular ring system, when we have the trans 1,4-dimethyl cyclohexane, it will favor the version in which all groups are equatorial. However, when we have the when we have the trans 1,4-dimethyl cyclohexane, the trans 1,4-dimethyl cyclohexane is going to favor both versions because they are ultimately the exact same stability. In each version, one methyl is axial and one methyl is equatorial. In the trans version, you can see that it's going to favor the version that is all equatorial instead of all axial. So it favors the equatorial version, whereas here, these two rings are going to be equally favored. Now, what happens when we change one of the substituents to be something different? In that case, we saw two equal methyls. Now, here we have a ring that has a larger group on it in an axial position versus the methyl here in an equatorial position. Now, when this goes through ring interconversion, you'll see that the methyl will still be up, but in an axial position, and the larger group will be in an equatorial position. So here, the ring is going to favor the side where the largest group is equatorial. So as said before, we're going to favor so that as many groups as possible as are equatorial, and also favor so that the larger group is equatorial. So with that in mind, let's do another practice. Which of these rings is the most stable conformation of trans 1-isopropyl 3-methyl cyclohexane? Now I want to note something. Based on the question of this problem, we know that we should be looking at a trans ring. So first, let's identify which of these rings are trans 1-isopropyl 3-methyl cyclohexane. Here, our ring is indeed at position 1, 2, and 3. This is an equatorial down isopropyl. And this methyl is a equatorial down methyl. Remember, you can always draw the axial position to help you realize if that equatorial is up or down. So these are both down, meaning they are not trans. This is a cis ring. Similarly here, this is axial up and axial up, meaning they also are cis and not trans. So both A and C are not even trans rings. When we look at options B and D, you'll see that this one, the big group, the isopropyl group, is equatorial down. And here, this is axial up. So we have an up and a down, making this a trans ring. Here we have a equatorial down methyl, and then axial up isopropyl. Again, down and up, making this the trans version of the ring. So here are two versions of the ring in the trans positioning. And we want to decide which is the more stable conformation. So the only difference here is that on our top ring, our methyl is in an axial position and our isopropyl is in an equatorial position. In option D, our methyl is equatorial and our isopropyl is axial. So remember that we want to stabilize this by putting the larger groups in the equatorial position. That means that between these two rings, option B is more stable because the larger isopropyl group is in the equatorial position.